Okay, thank you very much for the introduction. Let me go ahead and begin. Uh, we are living in an age of big data, and artificial intelligence is doing things like telling us what to watch next on Netflix, putting our hardworking game show contestants out of work, filtering the email that we read, and really controlling our interaction even when we shop. And it also filters the information that we receive from the world in terms of news or search results. But despite its omnipresence in our everyday lives, it's often a black box. And we don't necessarily want that to be the case. I think many people would say, and it's a fairly unobjectionable statement, that AI should be interpretable. But if we want that, I think we need to measure what we mean by interpretability. And so that's what I'm going to talk about today. I'm going to talk about some work that we've done to try to measure interpretability. And I'm going to talk about this for two particular families of methods, unsupervised methods and supervised methods. And before I jump into that, I want to say that interpretability is big, and I can't cover it in a short talk. And I'm focusing on my own work because that's what I know best. But if you're interested in this sort of thing, there are lots of resources out there. One good survey that I heartily recommend is Towards a Rigorous Science of Interpretable Machine Learning from Finale Doshi Velez and Beam Kim. And it goes through the entire ecosystem and all the levels of interpretability, going from simple functionally grounded evaluations, and we'll talk about some of those today, up to full human-centered application grounded evaluations. And the general flavor of why I think that interpretability is so important is that this is a way that we can augment the natural abilities of humans with the exciting opportunities of artificial intelligence to put the best of both worlds together and not replace humans, but to make them more effective, more productive, and to replace drudgery with creative excitement. And if you haven't gotten enough of me today and you want to know more about interpretability, you can check out my YouTube channel. We have a tutorial that I did with Chin-Hao Tan at NACL last year where we go over all of this in a lot more detail. Okay, so let's jump into unsupervised methods for dealing with large data. Every second, 600 new blog posts appear, 34,000 tweets are tweeted, 30 gigabytes of data are uploaded to Facebook, and it's unstructured. There's no XML to tell you what it means. And a common problem is to try to figure out what's going on in all this data. This is true for intelligence analysts, brand monitoring, journalists, humanists. You're trying to figure out, hey, what went on either in a day's worth of news or in all of the works of Lope de Vega. And a common solution is to use some sort of machine learning to get a sense of what happened in that data set. So we're going to use a tool called topic models to try to deal with this, and I'll talk about some of the work that we've done to apply interpretability analysis to this method. So a topic model takes as input a whole bunch of documents, and you tell it, hey, give me K topics. And it will give you K topics, and say if you run it over the New York Times over a decade, and you ask it for 50 topics, 3 of the topics will look like this. One is a technology topic, one is a business topic, and one is an arts topic. But the question is, how do you know if this is good? So in some joint work with Jonathan Chang, we provided our thoughts on how you should evaluate if this sort of result is interpretable. Does it make sense to a human user? But the alternative is something different. So how were people evaluating these models before? So what they did is they did held out likelihood evaluation, where you have this data set, you fit some models, and then you have some held out data, and you see how likely does each of the model fits think that the held out data are. And the higher the probability, the better. And so this may be familiar to you. And so if you compute the likelihood of a model, you have some training data. you use that data to infer some parameters of the model, latent variables, and then you test on your held out data how probable is that held out data, and higher numbers are better. But does this actually make sense for the kind of things that you use topic models for? And our argument was, no, it doesn't make sense. This isn't like a language model where you're trying to predict the next word. In those sorts of applications, held out likelihood is really useful. It's a great idea. But for these unsupervised techniques, you don't really care about next word prediction. If you take a look at any of the papers that people have written on the subject, you'll see a figure that looks like this. It's showing that the underlying topics made sense, and that you can tell a story with these results. And this is true even if you're not looking at English. It's also true if you're not looking at a natural language at all. So how can you actually evaluate whether this sort of result, this sort of output of a model makes sense to a human? So what we proposed is you take the topic and then and the highest probability words from that topic, and then you insert an intruder word into that topic. And our thinking is that if the user can detect that intruder word, the underlying topic made sense. Now, hopefully, you can kind of see how that would be. If the underlying topic were just 4 or 5 random words, then if you put one more random word in there, you wouldn't be able to tell what the random word was. But if the underlying words all made sense, then you could detect the intruder word with high probability. Okay, so this is a really important point. I'll pause here for questions or clarifications. Moving on. All right, so I set up this contrast between the old way of doing evaluation and the new way of doing evaluation. So let's put the old way of doing evaluation on the x-axis and the thing that we proposed on the y-axis. So now we can see if there's a correlation between the two. And there is a correlation, but it's a negative correlation, which is kind of surprising. And so this suggests that as your model gets more complex, the interpretability actually goes down. And so if you were using the traditional measures of machine learning models to evaluate these sorts of models that we use for human understanding, you're going to favor more complex models that are actually confusing to the users that they're supposed to be serving. Okay, so this was a long time ago that we did this work, and a lot has changed since then. Here is a brief overview of the sorts of things that people have done in the years since. And because this is a short talk, we won't be able to go into these in great detail. But what I want to do today is focus on automatic methods that purport to correlate with the human-centered metrics that we did. And so probably the most notable of this is some work by Jaehan Lau and Dave Newman and Tim Baldwin, where they basically came up with a formula that they showed correlates with the measurements that we did from humans. And one of the nice things is to come out of this is that basically every new topic modeling paper since then has used something like this for their evaluation. And this is true even as we've moved into neural models. So we wanted to revisit the question. So this is work with the great student Alexander Hoyle at the University of Maryland. So we set up this new way of doing evaluation. People have adopted automatic versions of this. Does it still work? And so he did this really exhaustive survey, and so this is too small for you to read, but I'm just focusing on one column here of all of these new neural topic modeling papers that have come out in the last couple of years, do they do a human evaluation? So this column here, and the answer is no. It's always no. Nobody is doing human evaluations anymore. And so they are looking at coherence, this automatic metric that purports to correlate with the sorts of metrics that we proposed. And so now we can compare for various models. Are you still doing better? And so here are 3 models, and in 3 columns. And so on the left-hand column, you have the automatic metric. And so here we have this new variational autoencoder that you can use for topic modeling to get summaries of your data out of that. And there's a clear winner here. It's doing better than these other approaches. It's the new fancy thing. And so, yeah, people can get publications out of this. But if you actually go back and ask humans which kind of output they prefer, there isn't a clear winner. And sometimes the really old 2004 Gibbs sampling LDA in blue does better than these fancier models. But maybe you don't really believe that. There's a lot of overlap in the distribution here. Yeah, you should be skeptical. Maybe there isn't a clear winner, but that's really the takeaway of this paper, that there isn't a clear winner, that if you do a human-centered evaluation, we haven't definitively improved over the approaches that were first introduced 20 years ago in 2004. And so the takeaway here is that all that passes automatic evaluations is not golden. And so if you want to have interpretable models, you should actually measure that with humans. OK, so that's a brief introduction to some work that we've done on unsupervised models. I'm now going to turn to supervised models, unless there are any questions. OK, so yeah,
sorry.
so I talked. Yes.
There are actually a couple of questions we have here in the chat.
OK, all right.
One's from a little bit earlier in the talk. So you are only using intruder words from other topics, like topic 2 or 3, not like a random intruder word?
Yes, exactly. So high probability words from other topics. I see a make sense from Michael, but I'm not seeing these other ones. So please do keep interrupting as more come in. OK, yeah, so continuing on. So we talked about unsupervised models that are trying to model a joint probability distribution over some latent structure Z and your data. But what about if you're trying to predict and answer Y from your data X? And so unsupervised models discover structure in the data, these topics that I showed you, but supervised models reproduce correct answers. And so the application that I like to look at is question answering. And so, for example, you have a question, which parts of the Earth are included in the lithosphere? And your system needs to predict the correct answer to this question, crust and rigid uppermost portion of the upper mantle, as the correct answer to that question. And so you may have seen this on, say, Jeopardy, where Watson took on Ken Jennings and Brad Rutter. That was a tour de force performance by IBM. Very jealous that they were able to do that. And so we're going to work on question answering as well, but we're going to change it a little bit. Instead of being able to answer a question when it appears in its entirety, we're going to do something a little bit more complicated. And hopefully, I can convince you that it's a good idea. And so the setting is going to be a little bit different. Instead of getting an entire question all at once, you're going to get a question word by word, and you're going to decide when to answer the question when you have enough information. And so this is easier to show with an example rather than trying to explain it. So I'm going to read a question and think about when you could answer the question. Okay, here's the question, and think about when you could interrupt, put it in the chat when you know the correct answer. The Swiss-Italian architect Pietro Antonio Solari built several fortified towers in the city, which often vied for power with its northern rival Tver. A ruler of the city prevailed in the Great Stand on the Urga River. A prince from the city was nicknamed for winning a battle on the Don River, partly because a ruler of the city married Sophia Paleogina, the niece of the last Byzantine emperor. The city styled itself the Third Rome after the fall of Constantinople. Another prince of the city stopped paying tribute to the Mongols in 1476, ending the Tartar yoke. The Grand Duchy headquartered in the city came to an end in 1547 with the ascension of Ivan IV, who made it his capital. For 10 points, name the city where Ivan III renovated the Kremlin, the capital of Russia. And so these questions are really long, and they're complicated. And they go from really difficult at the beginning to easy at the end. And so excellent, yes. Thank you for playing along, Louise. And so at the beginning, you really have to know a lot about Moscow to get the answer right. But most people recognize that the capital of Russia is, of course, Moscow. And so the earlier you can interrupt the question, the more you know about the subject. Okay, so with my former student Mohit Iyer, who's now a professor at the University of Massachusetts, and we built some systems that could play this game. We built a system that took on people who won a lot of money on Jeopardy. Our first outing ended in a 200-200 tie. The humans claimed that the computer lost because the computer shut down after playing 40 questions and refused to continue for a tiebreaker. We eventually did beat some humans, fairly strong humans who are some of the best trivia players in the world. And so I'm not going to talk about that today since there are other, that's kind of irrelevant to the question of interpretability. But what I want to talk about today is the human aspect of some of these competitions where we took on these really top-notch humans. And so for our exposition matches, we built a stupid little debugging screen just to make it clear that we knew what was happening and to diagnose problems that cropped up. But everyone loved looking at this debugging output because it kind of gave you some idea what the computer was thinking. And we played against 4 liberal arts majors here, and they were able to get a much better sense of what the system was doing and what the system was capable of than even senior undergraduates in my classes could do after a whole semester's worth of learning about natural language processing, machine learning, and AI, and all that. And so this gave us an idea that maybe the fun thing that we should be doing is, instead of having humans versus computers, maybe we should have humans and computers work together. And if we could explain what the computer is doing to the human, maybe we could get the best of both worlds. And part of our motivation was centaur chess. So after Kasparov was defeated by, again, IBM in one of their famous exhibition matches with Deep Blue, they built systems where humans and computers could team up together to play chess. And for over a decade, the best chess player in the world was neither a human nor a computer, but a human and a computer working together. And for all the talk about AIs taking over, I think this is the kind of world that I want to live in, where humans and computers are working together on some task. But if you want to work together, you need to communicate. So again, going back to what I talked about at the beginning, how do you actually measure how good of a team relationship do you have and how good is the communication? So we built an interface for people to play this Centaur Quiz Bowl, this crazy long interruptible question answering task that I talked about before. And so the way this works, a question comes in and the computer tries to figure out the answer and it communicates what it's thinking. So here's the overall screen. Let's zoom in on individual components of that. So first off, it shows what it thinks the answer is. And so you have the top in guesses coming out of the system with some score next to it. So it thinks that the answer is Congo River, but the score is kind of low, so it's not super confident. It also shows you the question as it's coming in, but it also highlights what it thinks are the most important words in the question in figuring out that, hey, maybe this could be Congo River. I think that because I see Kisangani. In addition, you also see things that it has seen at training time, previous questions, Wikipedia pages, things like that. It shows that to the user and again, can highlight the words that it thinks is important from that. Okay, and so I have been talking generally about humans, that we want to have humans interact with AI systems and we want to measure how well humans do, but that's pretty general. Let's be a little bit more specific now. Let's actually consider two different groups of humans, trivia nerds and crowd workers on Mechanical Turk. And so the trivia nerds are used to doing this sort of thing. They do it for fun. They are pretty good at it. But Mechanical Turkers, this is probably the first time that they've ever done anything like this, and they are not super familiar with the task. So let's see which explanations help whom. Okay, so here we have the accuracy. And so obviously the experts are better than the novices. So the vertical line here is the average over all conditions. And then we turn off each of the conditions one by one. And so you can see that each of the different kinds of explanations helps a little bit. So the cyan box is always a little bit higher than the red box when it's off. But you can see that novices are helped quite a bit more than the experts. And the biggest thing that helps the novices is the evidence. So like showing Wikipedia pages really helps the novices a lot more than the experts. For the experts, actually showing the highlighting what the system thinks is most useful in determining what the answer is, that helped the experts a little bit more. Okay, so that was kind of a binary analysis of what's going on in these questions. Let's dig a little bit deeper. And so we can treat this as a mixed effects model. We can run a regression to try to predict whether a user is going to get the answer right or not. And so the way this works is each of the conditions becomes a feature to this regression, and you try to predict the outcome. And if you have a positive coefficient for the resulting regression, that means that it helps. If you have a negative correlation, that means that it hurt. And if you have a small coefficient, the system didn't really detect much of a signal from that at all. And so Dan in the chat asks, are these general trivia experts or trivia experts at a specific topic? They're mostly general experts, but they're people who are familiar with the task. And so like some people may be good at a particular type of trivia, but they've signed up for the task and they're going to be better at just about every kind of trivia than a random person on Mechanical Turk in all likelihood. And so let's take a look at the coefficients. So just looking at the individual types of explanations, we see the same thing that we saw before. Evidence helps the novices a lot more than the experts. Highlighting helps the experts a lot more than the novices. But now we can take a look at the combinations of different explanations together. And we can see synergistic effects. That the experts, if you turn on guesses and highlighting, you get an extra bonus as well. The expert can put these two explanations together and improve their accuracy even further. And indeed, highlighting plus evidence, putting those two things together gives you the biggest synergies. The novices, on the other hand, don't really have this sort of synergy. They get most of the assistance from seeing the evidence and not much synergy beyond that. And this suggests that they're kind of overwhelmed, that they only have so much mental processing power, and they're getting cognitively overloaded by all of the stuff that they're seeing, and you don't see any huge help beyond that. Okay, so I now want to talk about extending this a little bit further, and this again is work by my excellent former student, Shurfun, who is a postdoc at U Chicago at the moment, and will be starting a tenure track job at a place to be announced very soon. And so let's think about this a little bit more. So let's say that you have a human and you want to help them at some task. They get some score at this task, and let's again say it's question answering, the same crazy quiz bowl task we talked about before. And the computer points out the answer, has some explanation of what it thinks the answer is, and it can try out different ways of explaining it. And so which of those explanations help the human the most? Let's say it can explore around, see what score it gets compared to the baseline, and then that becomes a reward that goes back and say, hey, do more of that, explain like that. And so we can take this exploration approach where the system is learning what kind of human is it working with, and how can you best explain the thought process of the AI through this cooperation. So this is exactly what we did. We built a bandit-based system to optimize these explanations. And so I'll show you more results in a second, but I first want to focus on what if the AI just played by itself. So the AI is pretty good. You have time, question number on the x-axis, and how many points it got on the y-axis. And so the AI by itself does pretty good. And so we want to do better than that, because like if a human computer team can't do better than that, then why have the human involved at all? Like, just forget about the human, let the AI take over. Thankfully, that is not the case, at least for this task. If you actually learn what to show people, you build a tailored explanation to everyone, that does better than the AI by itself, and also just showing all of the explanations constantly. So people do get overloaded. You want to tailor your explanations for the specific person that you're communicating with, and that could indeed be situation specific. You might want different explanations when you're on your smartphone versus when you're at a big multi-panel display. And we can learn how to tailor explanations based on situational preferences, situational needs, using this sort of approach. And indeed, it's better than showing everything all the time, which is a pretty strong baseline, actually, and that in turn is better than just the AI by itself. So these are fun and games, but can we connect this to anything more important, more realistic? And so I'm going to talk about a line of work from 3 excellent students, now faculty at New York University, Alvin Grissom, now faculty at Haverford College, and Hyojung Han, who is still a student at the University of Maryland. And so they're working on a task called a simultaneous interpretation. And the way this works is that you are at a high-level event, and you're getting real-time interpretation. So this is what happens at the European Parliament or the United Nations. You have an earpiece, someone is speaking in Japanese, and a really talented translator is translating that Japanese into English so that you can hear and understand it in real time. And so computers are not trusted to do this at all. In these high stakes settings, you don't want to have a wrong translation. You want to be able to back channel if there's some ambiguity. And that's not to say that computers can't help, but we just haven't figured out a way to put them in the pipeline. But it also looks a lot like this crazy quiz bowl task that I talked about before. You have words coming in one by one, in this case, the Japanese speech, and the interpreter needs to decide after every word, am I confident enough to give an answer, to give a translation? And so it has the same kind of API profile as the task that we talked about before. And so let's think about how we could evaluate this. Let's say that you're a contestant on a Polish game show, and you have access to a simultaneous translation system. And your job is to answer the question before the opponent. And so if the better the translation system is, the more points that you will get. And so this is the approach that we took to evaluate the quality of these simultaneous interpretation systems. We have the same explanation comes in. In this case, it's an explanation not just of a QA system, but of a translation system, and showing the output of a translation system and asking a human or a QA system to answer the question based on that. And so if we keep the QA system constant and only vary the translations, this serves as a way of evaluating how good the underlying translations are. And we think that, so this is a weird way of evaluating translations, but one of the reasons that we're arguing for this is that, one, Blue, the traditional way of evaluating translations, basically just says that you should wait as long as possible. You should never interrupt to translate. Just wait as long as possible, and your translation will always be better. There's some diminishing returns to that, but it's a good translation. But evaluation metrics like this require you to have gold translations as well. We just need to have the answer to the question, and we can just check if the answer is right. So it's a little bit cheaper to do this evaluation. And so if we do the evaluation that we proposed, we get a clear win if you wait around 9 words before you start translating. This gives the highest score on the question answering task. And again, you only need to know the answer to do this evaluation. It also highlights some of the problems that can happen in these large language model based translation approaches. You often get under translation, that these systems just kind of put out low probability, or sorry, high probability, but low information strings. And so things like, and of course, this is in the, and so it kind of vamps like that without getting new content. And if the probability of the correct answer isn't moving, that shows you that under translation is happening. It also can show you when hallucinations are happening, when the probability of a wrong answer jumps up quite a bit. Okay, so we have some good questions in the chat. I will come back to Lime and things like that at the end, because that's more of a general question. But Jen asked, do these word counts include stop words? Yes, they do. So a word's a word, and so we're including that. For this sort of thing, it's hard to not include those, because often they're in part of important phrases like Ministry of Defense or something like that. And so like of is a stop word, but it's in a very important phrase. Okay, so as I begin to wrap up, I want to reiterate that AI is becoming more and more important to new technologies and to our daily lives. And I think that if we want to live in a world where artificial intelligence plays a useful part of our day-to-day existence and is not replacing us or threatening us, we need to make it less of a black box. And AI should be interpretable. But many of us are engineers, many of us build things, and it's hard to aim for a particular quality, a particular aspect of what we're building if we don't have a way of measuring it. And I put forward some ways of measuring interpretability with real humans in the loop. I don't think that they're perfect, but I hope that they begin a good conversation about the kind of measurements that we could have. And I think that this is a more important conversation to be having, because if we measure interpretability and it's a property that we want these systems to have, we should invest in metrics that reflect the world that we want to live in, where we're collaborating with computers that explain themselves, that don't make stuff up, that are useful for the things that we want to use them for. And so if we measure that, I think we're going to have a much better future. Yeah, so to make that happen, we need to make it easier for human-driven evaluation, to have better models of individual users, drawing on tools from psychology like item response theory, and yeah, focus on tasks where there is a natural collaboration between human and AI. And so I talked about understanding large text corpora and question answering, but this also comes into play in things like fact checking, media consumption, for collaborative generation of art and stories. And so I think there are a lot of places where you could create tasks that explicitly measure collaboration. Okay, that's all I have. Thank you for your attention. I'll now go answer Ken's question, but if folks have more questions, feel free to type them in the chat. So Ken's question is, thoughts about using methods such as, I think, shapely value. It says line for interpretability, or other methods I'd recommend. So this is covered in more detail in our NACL tutorial. Please do check it out. We go over all of these things in there as applied to text. Yeah, so Lime is great, and so this is Ribeiro et al. I kind of disagree with some of the measurements that they did, and so if you look at the Lime paper, they were using the explanations for engineering features to improve a text-based classifier. And so that kind of goes against some of the philosophy that I put out here. So here you're using interpretations to show it to a human to help a machine get better. And so that kind of goes in the wrong direction, at least in my mind, that we don't want the machine making the final decisions. We want a human making the final decisions. So you should measure how useful are the explanations in improving the human's ability, not measuring how useful the explanations are for improving a computer's ability. But that being said, the actual technique that they used in the perturbations for generating those explanations, yeah, that was really seminal work. Yeah, so Brenton asks, there's a data science who's been on a winning streak on Jeopardy recently. I wonder how she'd do with computer assistance. Yeah, so we've had a lot of collaborations with folks who have been on Jeopardy, and so there are a number of folks like that. And so I think that if you're good enough to do really well on Jeopardy. The computer is not going to help on too many questions, but it would certainly, I think, help on things that are kind of outside your areas of expertise, and to help increase your confidence in double checking that, oh, I think this answer is actually Benjamin Harrison, and oh yes, okay, and the computer agrees with me, I can be more confident. So I think in terms of confidence estimation and things like that, it's a really useful tool. Thank you very much for having me. And yeah, more stuff is available online if you're interested.